Finally, let's take a look at a third innovation area, an area surrounding technology and protective relaying itself. A number of the higher-end digital protective relays today will include multiple settings group capability, essentially allowing the operator to set one selective coordination curve for one situation and a second for another. Because of the lowering cost of electronics, this type of capability has now been embedded into some of the lower-end trip units and even in some integral trip units that are part of low voltage and medium voltage power circuit breakers. The Eaton offering here is called ARMS, Arc Flash Reduction Maintenance System. This actually is an option on low and medium voltage integral trip units for circuit breakers. And you can see in this picture that we have in the upper left-hand corner of the integral trip unit the capability of turning on a maintenance mode and selecting 5 different instantaneous settings. When I want to set the breaker or the tripping system up so that if someone was working in downstream energized equipment, the trip unit would react differently and in fact trip instantaneously. Obviously, the lower clearing times associated with an instantaneous trip will reduce the downstream arc flash energy. There also is a blue indicating light on the trip unit showing that the relay is set in the ARMS mode. Of course, a door-mounted switch and light can also be provided if required. Let's walk through an example to demonstrate how the ARMS multiple settings group capability works. What I've shown here is coordination curves for a unit substation. On the left is the setting that you would have for a selectively coordinated system. The main breaker is shown by the green curve and the feeder breakers are shown by the purple curve. You can see both have a short time delay setting. And as you can see on the left-hand curve, if I had a arc fault current or an arcing current of 5600 amps, I would be in the short time delay setting of the feeder circuit breaker. That would result in a hazard risk category of 3 or 11 calories per centimeter squared. So if I actually had someone working downstream of this substation, I could set this trip unit into a maintenance mode using the ARMS capability. What happens then is that the feeder breaker curve shifts over to the left as shown on the right in the pink colored curve. And in this case you can see moving that curve over with the same arcing current would reduce the hazard risk category down to 1 or less than 4 calories per centimeter squared. It's important to note here that I may be sacrificing coordination with this setting. Difficult to see, but on the far left of both curves is a brown colored line showing the largest motor on this system and its starting curve. And as you can see, when I'm selectively coordinated on the left, I can start that motor into that feeder circuit breaker. But on the right, in the ARMS mode, you can see that if I tried to start that motor while I was set in the ARMS position, my feeder breaker would trip. So I've lost selective coordination. I'm effectively trading coordination for people safety. If someone's working in energized equipment downstream, it's probably a good trade. So this brings us back to our earlier example of an integrated paper mill in the Pacific Northwest of the U.S. You remember in this case, because there was no secondary main breaker in the substation, after the site conducted an arc flash study, they found that racking a breaker off of the secondary bus was a very dangerous situation. In fact, the calculations from the NFPA 70E showed that it was unapproachable, or there was no protective equipment a service personnel could wear and be safe. Because this facility operates in a process environment, it was quite frequent that the feeder breakers on the low voltage switchgear would be racked out as a part of the lockout tagout procedure while the rest of the substation remained energized. Because the substation was existing, the facility was actually landlocked. There was no physical way to add a secondary main breaker. So they decided to move forward with some of the new technology we've shown you, installing a miniature vacuum circuit breaker with an integral trip unit in the primary of the substation, essentially replacing the switch but leaving the load break disconnect in the primary assembly. It's interesting to note that this breaker is actually tripped from two different places. One via a 5051 overcurrent device that's mounted in the primary assembly itself, which actually trips the breaker through a lockout 86 relay and a shunt trip, and the other via the integral trip unit in the breaker connected to secondary CTs in the secondary switchgear bus. We show a photo at the right of the before and after picture, and as you can see, the new miniature breaker fit neatly into the existing assembly, and the facility decided to leave the load break switch because it was a clear visual indication and could be used as a safety disconnect in the event of a lockout tagout requirement for the entire substation. Below, I have shown the results of the revised arc flash study in both the before and after scenarios. As you can see, the addition of the vacuum circuit breaker on the primary of this substation greatly reduced the arc flash boundary, the calories per centimeter squared, and the hazard risk category associated with the main secondary bus in this substation. It's interesting to note here, when you look at this diagram, that the integral trip unit in the primary vacuum breaker is actually tripping from secondary current transformers and protecting the secondary bus. The reason for this selection is, as discussed before, the fact that the integral trip unit, working in conjunction with a linear trip actuator with this breaker, enables faster clearing times, typically 3 cycles. The integral trip unit was also installed with the ARMS feature, as we discussed before, allowing operators in the maintenance mode when they were racking secondary breakers on and off the bus to lower the incident energy via making that tripping system work instantaneously in the event of a fault while the breaker was being removed or inserted. What we've shown here is pictures from the actual installation. On the left is the new miniature circuit breaker installed, showing the secondary control terminations. In the center is a picture of the breaker and the existing load break switch, and on the right is a picture of the assembly with the door closed. Note that there's a control box on the front of this assembly that was a part of this retrofit that includes the 5051 device protecting the primary bus, and also a breaker control switch, the lockout relay, breaker indicating lights, and also a switch and lights for the ARMS system. Okay, so far so good, mission accomplished. But I'd like to bring up an application issue that surfaced a number of years ago that we had to deal with in this specific instance. Early applications of medium voltage vacuum circuit breakers applied in close proximity to substation transformers have yielded some somewhat disastrous results. I've shown here a photo of a failure on a transformer that was very closely mounted to a vacuum interrupter, and in this case there were flash burn marks on the transformer, and after it was returned to the factory it was determined that there was a coil-to-coil failure. After reviewing the system dynamics, the cause of the transformer failure was determined to be the proximity of the VI or vacuum interrupter to the first winding of the transformer. And it came down to a characteristic of the VI itself, a characteristic known as current chop. Chop current is actually a published parameter that most all VI manufacturers will offer, and it actually is the current, a fairly low value, perhaps 4 to 8 amps, in which the VI interrupts instantaneously. So after you ask the interrupter to open, because it interrupts in vacuum, as current drives towards the chop current value, let's say 5 amps, it will go from 5 amperes to 0 instantaneously. You can see from the 3-phase current trace on this slide the impact of chop current. As the current drives towards 0, when it gets to the chop value, let's say 5 amperes, it instantaneously goes to 0 amperes. Of course, when switching into a purely inductive load, for instance a transformer winding, When you drive current to zero, voltage has to go somewhere, and in this case it goes into the sky. As you can see from the voltage waveforms on this same analysis, I have peak voltages of close to 150 kV. In a 90 kV BIL transformer, this is beyond the device's rating, and that's what will drive you towards failure. Fortunately, resolving this application issue is fairly straightforward. We can install a resistor capacitor snubber network on the output of the vacuum circuit interrupter, which will reduce the voltage transients that occur when the VI opens. In this case, I've brought the transients down to 30 kV, which is well within the rating of the transformer. It's interesting to note here that this issue is really directly linked to the proximity of the vacuum interrupter to the transformer inductive load. As I add resistance, either in cable impedance or if I was interrupting a fault, impedance across an arc, then that will effectively reduce the voltage spikes that will be seen when the VI opens. For illustrative purposes, we've shown here the RC snubber network that was installed in this specific application. Again, the application of this VI really is only an issue when it's in close proximity to the transformer. It was actually mounted in the assembly as a part of the retrofill activity on the load side of the vacuum breaker. It was designed specifically to the chop current of the VI and the breaker itself, and via a transient analysis, the sizing of both the capacitor and resistor were fairly straightforward. Snubber design is obviously a technical subject unto itself, and we intend to take a look at this a little closer in a separate Launch and Learn. But for now, let's push forward. We spoke earlier about installing a vacuum circuit breaker in an existing assembly, but what if it was a new assembly, either for an existing substation or a new project? In this case, we can apply a medium voltage switch over breaker, or an MSB. This assembly is functionally identical to the retrofit assembly we reviewed earlier. It has a load break switch, visible blade in the top, and a fixed mounted vacuum circuit breaker in the bottom. I've shown on the left a section view of this MSB assembly, and if you follow the red lines from the incoming line in the upper right, you can see the terminations for the 15 kV power come in to the incoming bus, and you follow the arrows up and through the load break switch, and then back to the rear of the assembly through current transformers mounted on the bus, and then through the fixed mounted vacuum breaker and out to the load. You can also see in this assembly other items, including the snubber in the lower right, and in this case we have an application that included the requirement for a control power transformer at the upper section and also a lightning arrestor. Here we show some photos of this same assembly. It's available in either a NEMA 1 or an outdoor NEMA 3R enclosure. And you can see from the pictures that from the rear of the cabinet the snubbers are mounted in the lower section, and you can see the bus runbacks with the current transformers. And finally on the right from the front, there's a door-in-door application that allows easy access to the primary protective relay, breaker control switch, and indicating lights. Here we're showing you essentially the same MSB medium voltage load break switch over fixed mount vacuum breaker assembly, but this one was applied in a greenfield site. Actually, in this site there were 12 unit substations. Some were low and some were medium voltage secondaries, but each applied an MSB assembly on the primary. In this case you can see in the upper front compartment also a lightning arrestor, and also in the lower rear compartment the snubber network, which is integral and part of the assembly shipped from the factory.